So thank you very much. Good morning, everyone. So indeed, in this talk, what I want to do is to address the question of whether we can detect a signature of the quantum origin of the primordial perturbations. So I have organized the talk in the following way. The first part will be devoted to some quick motivations, and this will be connected with the talk by Andy yesterday, I think. Then I will explain very briefly the theory of cosmological perturbation of quantum mechanical origin. And then I will go to the two main questions that I want to address here, namely whether the perturbation can be seen as a quantum system or whether we can describe this system effectively in terms of classical terms or stochastic terms, if you prefer. And then I will also try to answer the question of whether we can find a direct signature of the quantumness of the cosmological perturbations. So let me move to the first part and let me give the motivations for the talk. So, well, we all know that according to inflation, the perturbations originate from the quantum fluctuation of the gravitational and scalar fields. Scalar fields, of course, we think scalar fields are the inflaton field. And we think that those fluctuations that are present in the early universe are then amplified by the mechanism of gravitational instability and then are stretched on very large distances, on cosmological distances, by the expansion of the universe. So the first remark is that this is, of course, a very strong statement because it means that everything that we observe in our universe, from galaxy, clusters of galaxies, CMB anisotropies, all that are nothing but quantum fluctuations amplified to cosmological distances. And well, it seems that despite the fact that this is a very strong statement, this statement seems to be correct simply because all the consequences that can be inferred from making this assumption seems to fit well the data. We know that the predictions that we can derive from inflation are in good agreement with the astrophysical data that we have at our disposal. So in some sense, this gives an indirect confirmation of the quantum mechanical nature of the perturbations. But here we would like to address a more ambitious goal in some sense, which would be to study whether we can find a direct signature in the sky of this quantum mechanical nature of the perturbations. So this is the motivation of this talk. Now let me discuss briefly the theory of cosmological perturbation of quantum mechanical origin, since this is the tool that we need in order to address the motivation that I have just described for you. Here I just repeat what I said. The perturbations are supposed to originate from quantum fluctuations, and therefore this means that the metric tensor, which describes the gravitational field, can be expanded in some sense in the following way, according to the equation that you can read on the top of the slide, namely homogeneous and isotropic piece, which is of course the Friedmann-Lemaitre-Robertson-Walker space-time or manifold, plus a small, so we have a perturbative treatment in mind, inhomogeneous fluctuation. This is why this piece depends on X. So homogeneous small perturbation, which in addition is a quantum operator, and this is why I have written a hat on top of it. And of course, this is the same for the inflaton field, for the perturbed inflaton field. So really what we have in mind here is that there is a homogeneous and isotropic background space-time, an expanding space-time, and on top of this background, we have small ripples, small fluctuations that are inhomogeneous, so we go beyond the cosmological principle, and that are quantum. It's a bit like in a crystal, where you have a classical crystal, and on top of the crystal, you have the phonons that are small quantum vibration of the crystal. So as we learned during the first day, we have three types of perturbations: scalar, vector, and tensor. Here in this talk, I will focus only on scalar perturbations, but it's not loss of generality at all, because I could reproduce the same discussion for tensor perturbations, for instance. But I will focus on scalar perturbations. And in fact, it turns out that, at least in this simple framework, scalar perturbation can be described in terms of a single quantity, which is curvature perturbation, zeta. So in this framework, zeta is a quantum operator, and it can be Fourier expanded, and it can be also expanded in terms of the creation and annihilation operator, as you can read on the screen. And the time dependence of the curvature perturbation is given by the time dependence of the creation and annihilation operator. So in Minkowski spacetime, of course, this time dependence is nothing but EI omega t. But here, our fluctuation live on top of a cosmological background, and therefore this time dependence is slightly more complicated. So let me also stress that this curvature perturbation is in fact directly related to what we see on the sky. In particular, it gives directly the CMB anisotropies on large scales. So now let me describe how the time dependence of this curvature perturbation, or equivalently creation and annihilation operator, can be calculated. In fact, it can be calculated from the Hamiltonian of the system, which is written on the slide. So before I explain why we have this Hamiltonian, let me stress that it is really derived from first principle, namely you take the Einstein-Hilbert action plus the action of a scalar field, you expand at second order, since you want the equation of motion to be first order, you plug the expansion of the field in terms of creation and annihilation operator, and you end up with this equation for the Hamiltonian. So this Hamiltonian, as you can see, is made of two pieces. The first piece is just a free term. So this is the Hamiltonian that I would get in Minkowski space-time for a massless scalar field. So it's just a collection of free harmonic oscillator. I have an infinite collection of free harmonic oscillator as revealed by the integral of wave numbers. And I have another piece, which is especially interesting for Earth. And you see that this piece represents the interaction between the quantum fluctuation that we are studying and the classical background. This term is in fact made itself of two pieces. There is the first part, which can be as a kind of time-dependent coupling constant. So in this expression, A is the scale factor, and epsilon1 is the first slow roll parameter. So in the present context, you can think of epsilon1 as a function of the scale factor and its derivative. And the important point is that epsilon1, the important point is that this effective time-dependent coupling constant vanishes if the scale factor is as a vanishing derivative. So in other words, if the field lives in Minkowski space-time, where the scale factor in some sense is static, then this time-dependent coupling constant is zero, and we don't have the interaction term. So the presence of this interaction term is really related to the fact that this small fluctuation live on top of an expanding background. And then you have the second part, which is also interesting. In particular, you remark the structure K minus K. And in fact, this means that the corresponding particles are created by pair with opposite momentum, K minus K. So in fact, this effect, these inflationary mechanisms for amplifications of the initial cosmological perturbations, in fact belongs to a very wide and well-known class of effect. And the prototype of such effect is the Schwinger effect. So the Schwinger effect is the following. You take an electron and positron field, so a fermions, which is of course a quantum field, and you make it interacting with a classical source, a classical electric field. And because of this interaction between the quantum field and the classical source, you have productions of particles. So you, in some sense, extract particles from the vacuum because of the interaction between the classical source and the quantum field. And the effect is controlled by the strength of the source, that is to say, in that case, the amplitude of the electric field. And this is a well-known effect that was computed by Schwinger in the 50s. This is an interesting effect because this is one of the few effects in quantum field theory which is non-perturbative and which at the same time allows you to do exact calculations. And in fact, the inflationary mechanism for perturbation is exactly similar to that. What plays the role of the fermions are just inhomogeneous gravitational fluctuations. The source is the expanding space-time, the scale factor, if you wish, and the amplitude of the effect, so the two-point correlation function of the fluctuation, for instance, the amplitude of this two-point correlation function is controlled by the strength of the source, that is to say, by the strength of the expansions of space-time, which is the Hubble parameter. So maybe these mechanisms for inflationary fluctuation, which may seem at first sight a bit exotic, it takes place in the very early universe at very high energy scales, is from a quantum field point of view, very conservative one. It belongs to a well-known class of effects. We also have the dynamical Schwinger effect or the dynamical Casimir effect, which has been seen in the lab, and so on. Now let me discuss a little bit the initial conditions. So here you see a plot you are probably very familiar with. So on the vertical axis, I have the physical distances of the relevant quantities for our problem versus on the horizontal axis time, the logarithm of the scale factor, so the number of e-folds. And the colored lines, green, red, blue, and orange, are the evolution or represent the evolution of the Hubble radius during inflation and during the subsequent Big Bang phase. And the black line represents the physical wavelengths of a given Fourier mode of astrophysical interest today. So you see that,
Martin?
Yes.
There is a question by Swagat Mishra. Would you like to take it right now? So this is regarding your last slide. So regarding the time, I'll read the question.
Yes.
Regarding the time-dependent coupling of background with fluctuations, just
Yes.
expansion does not enhance the fluctuations on large scale. Acceleration must be necessary, isn't it?
No, I don't think so. Acceleration is necessary to, if you want to get a scale invariant power spectrum, it's true. But these mechanisms of productions of particles just needs a background which is dynamical. So just requires A to be not static.
Okay, thank you.
You're welcome. Yes, so I was saying that initially the perturbations, or the physical wavelengths of a given Fourier mode is, thanks to inflation and the fact that the Hubble radius is constant during inflation, is inside the Hubble radius. Then as inflation proceeds, it crosses out the Hubble radius, spends some time outside the Hubble radius, and then re-enters either during the radiation or matter-dominated phase, depending on the wave number. So this means that the important point here is that initially, in some sense, the perturbation do not feel the curvature of space-time, and so it's it feels no curvature, so it feels like in Minkowski space-time, and therefore it seems natural to assume that the initial state is the vacuum state or the adiabatic vacuum state or the Bunch-Davies state, as you may want to call it. And this is the standard assumption for the perturbations. And if we now try to understand a bit better this initial state and its evolution through inflation, it's interesting also to describe the system not in the Heisenberg point of view, but in the Schrödinger point of view. So in the Schrödinger point of view, you have a wave function for curvature perturbation, a wave functional, since it's a wave function which depends on an infinite number of coordinates in some sense. And you can always, at linear order in the perturbation, expand the wave functional of the perturbation as a product over the wave numbers of a wave function. So this is the equation that you can see at the top of the slide. And in fact, the Bunch-Davies state, it consists in assuming that your initial wave function for a fixed mode K is just the ground state of an harmonic oscillator. So it's just a Gaussian state. And you see that, so if I represent this Gaussian state or the ground state of an harmonic oscillator in the space zeta k, zeta minus k, it's just a circle, and you see that you have no correlation between zeta k and zeta minus k. So this is for the initial state, but as inflation proceeds, we have seen that the mode will cross out the Hubble radius, and the quantum state of the perturbation will evolve with time. And this initial coherent state, which by the way is the prototype of what a classical state is, because in quantum optics, for instance, you describe classical light in terms of coherent state. So if you follow the evolution of the system in phase space, a coherent state would be a small bump following the classical trajectory of the system without any dispersion. So, so from this initial vacuum coherent state, as inflation proceeds, the quantum state evolves in time and becomes a two-mode squeezed state. So the two-mode squeezed state is given by the wave function is given by the equation at the bottom of the slide. You see that there is a new parameter here, R, which is the squeezing parameter, and the state in the space zeta k, zeta minus k is no longer represented by a circle, it's represented by an ellipse. The width or the flatness of the ellipse is characterized by the squeezing parameter, R, which is increasing with time as inflation proceeds. And you see that because of the squeezing, we now have quantum correlation between zeta k and zeta minus k. So a remark in passing, you probably know that the CMB is probably the most accurate black body ever produced in nature, because we are not able in the lab to reproduce or to build such an accurate black body. And this property is probably true for the cosmological perturbations, because the cosmological two-mode squeezed state is a very strongly squeezed state. And by that, I mean that the squeezing parameter that I was describing before is typically of the order of 10 to the 2, maybe slightly less than that, 70 maybe. And while people in the lab fight to achieve are a few. So really by laboratory standard, I would say, the cosmological two-mode squeezed state is very strongly squeezed. Okay, so this is it for a short description of the cosmological perturbation. Let me now come to the main question, namely whether this system can be described effectively as classical, or if it's really a quantum system. So first of all, let me say that of course it's a quantum system. From the previous description, it was clear that I was using quantum mechanics to describe it. But what I am interested here is rather to understand whether a quantum to classical transition took place, or if you wish, a car is a quantum system since it's made of atoms which are quantum objects. But of course, nobody would attempt to describe the motion of a car using quantum mechanics, we know that it's well approximated by classical equation. And this is exactly the same question that I want to address here for cosmological perturbations. In addition, it's known that when astronomers analyze the CMB and isotropy, they never make use of the quantum formalism. They do it classically. So we want to understand how something which looks like a very quantum can be effectively classical, and whether this is true or not. So the interesting point is that, in fact, when you think a little bit about this question, you end up with a situation where you have arguments in favor of a quantum description, but at the same time, you also have argument in favor of classical arguments. And also, it may seem a little bit contradictory at first sight. I will try to explain why these two things are in fact perfectly compatible. So there are other arguments, but I have no time to list them. So let me try to go through what I have written on the screen. And let me start with the arguments that are in favor of a very quantum system. So the first thing is that a two-mode squeezed state is an entangled state. And we know that an entangled state in quantum mechanics is usually seen as the prototype of a state which cannot be described in terms of classical physics. In addition, it's also very well known that if you take a two-mode squeezed state and send the squeezing parameter to infinity, this two-mode squeezed state tends toward an Einstein-Podolsky-Rosen state, EPR state. And we know that Einstein and many other people after him use this state to describe the weird properties of quantum mechanics. So if you have a system which is placed in such a state, the immediate thought that comes to mind is that it's a very quantum system. In addition, another argument is that the quantum discord is large. So what is quantum discord? So quantum discord is a tool that has been recently developed by people studying quantum information theory. So it's a tool which allows you to decide basically whether a system is quantum or not. So the main idea, I have no time to enter the details, but the main idea is that you take your system and you divide it into two subsystems, two pieces. So you have a bipartite system, and you study the correlation between the two subsystems. If those correlations are quantum mechanical, you say that your system is quantum. If they are classical, you say that your system is classical. So the quantum discord quantifies the nature of the correlation of the system, if you wish. If the quantum discord is zero, then the system is classical. If it's not zero, then you may say that the system contains quantum correlation. And with Vincent Venin, we have recently computed the quantum discord, and you can see a plot of this quantum discord. So the two subsystems are mod K, mod minus K. So we compute the quantum discord between these two subsystems as a function of the squeezing parameter. And when you do this calculation, you obtain the blue curve. You see that when the squeezing parameter is zero, the discord is zero. So because initially we have a coherent state, as I said before. And as I said before as well, a coherent state is the prototype of the classical state. It's a classical light for people working or familiar with quantum optics. And therefore, it contains only classical correlation or no correlation at all. And as a result, the discord is zero. But as soon as the evolution during inflation takes place, the squeezing parameter increases. And as soon as the squeezing parameter is not zero, then the discord is not zero. So this calculation of the quantum discord, it seems to confirm that the system, namely cosmological perturbation, is indeed a very, or the quantumness of this system is very large. But strangely, we also have, as I said before, arguments that go in the opposite direction, namely that suggest that this system can be treated completely classically. And this was also mentioned by Andy Albrecht in his talk yesterday. And one of these arguments is based on the Wigner function. So let me quickly explain what it is. So a system, a quantum system or any system can be described classically or by means of a stochastic description if the following properties are satisfied. So let's assume that we have a given function A that lives in phase space. So here I have consider a four-dimensional phase space, Q, K, and Q minus K are the position of the mode K and minus K, and pi K and pi minus K are the conjugate momentum. So this is a four-dimensional phase space, and A that you can see on this expression is any function living in this phase space. And if a stochastic description is available, this means that the stochastic average of the quantity A is given by this integral, where W is a probability density distribution. And this is a valid description, which could mimic completely the predictions of quantum mechanics if the following conditions are satisfied. First of all, the distribution function is positive definite everywhere. This distribution function obeys classical equation of motion, and the stochastic averages always equal the quantum averages. If these three conditions are satisfied, in some sense, you do not need any quantum mechanical consideration to calculate stochastically or classically, if you wish, the predictions of the properties of the system. So let me go through these three conditions and try to see whether they are satisfied for perturbations.
Professor Martin, I
yes.
can. There's 5 minutes left in your talk, so just
okay. Okay, perfect. Thank you. So first of all, the positivity of the distribution function. Well, I should here mention that the distribution function in this context is the Wigner function. And this is satisfied for cosmological perturbation because the Wigner function of a cosmological perturbation is always positive. So let me elaborate a little bit on this question. So first of all, what is the Wigner function? In fact, it belongs to a larger class of quantities, which are based on the so-called Weyl transform. So the Weyl transform is it's a map, you take an operator and it returns a function in phase space according to the equation that is written at the top of the slide. So you see this Weyl transform is very roughly speaking, in a sloppy way, it's taking the Fourier transform of the mean value of your quantum operator, and it gives you a function in phase space. And the Wigner function is nothing but the Weyl transform of the density matrix of the system. And usually this Wigner function, so which can be viewed as the quantum equivalent of the classical distribution function, is not necessarily positive definite. In fact, this can be easily illustrated on the example of a Schrödinger cat. Here I have represented the Wigner function of a Schrödinger cat. So you take a wave packet located at the plus position, plus a wave packet located at the minus position. You compute the Wigner function. You see that you have two peaks, one on the left, one on the right, which correspond to the two positions of the wave packets. And in between, you have this oscillatory behavior due to interference between the two wave packets. And you see that the Wigner function can become negative. And this is why people believe, since interference is really something which is typical of quantum mechanics, this is why people believe that positivity or negativity of the Wigner function is in some sense a signature that something quantum is going on. But if you take now the Wigner function of the two-mode squeezed state, The two-mode squeezed state is a Gaussian state. The Fourier transform of a Gaussian state is a Gaussian, and therefore the Wigner function of a Gaussian state is also Gaussian, and therefore it's positive definite. So this first property is satisfied. Then you can show that W obeys classical equation of motion. In fact, this has nothing to do with the example of the perturbations, because it's true for any quadratic Hamiltonian. The Hamiltonian for the perturbation here, since we work at first order in perturbation theory, is quadratic. And for quadratic system, this is always true. And you can also show that any power of curvature perturbation would satisfy the fact that the stochastic average of this quantity is equal to this quantum average. So in some sense, you see that from this point of view, a classical or a stochastic description of the system is perfectly possible. Power spectrum, bispectrum, trispectrum, all that can be reproduced with stochastic averages and with a positive definite function. So just a remark on this question in passing, contrary to what is sometimes said, this has absolutely nothing to do with the amount of squeezing in the system. This is always true, regardless of the amount of squeezing in the system. Well, since I am running out of time, I skipped the justification for this last statement, and if you are interested, I can come back to it during the question session. So if I recap, a two-mode squeezed state has a Wigner function which is positive, and therefore there is, in quotation mark, no need of quantum mechanics. The system can be described in classical terms. But we have seen before that the system is placed in an almost EPR Schrödinger entangled state, which is known to be the prototypical non-classical state. So hence the question, how can these two statements be true at the same time? And in fact, what is, at least what I find interesting and funny, is that exactly the same situation has been discussed in the past by John Bell. You know that John Bell has written a well-known book, Speakable and Unspeakable in Quantum Mechanics. And in one of the chapter 21, if I remember correctly, there is a paper which is entitled EPR Correlation and EPW Distribution. EPW stands for Eugene Paul Wigner, and EPW distribution is nothing but the Wigner function. And Bell tried to study exactly the same question. Also, it was not at all in the context of cosmology. Namely, he was wondering whether, if you have a system which has a positive definite Wigner function, he was wondering whether this system can violate its inequality. And it's a long story, so I cannot, of course, reproduce or explain this story here. But it turns out that the conclusions of Bell is that if the Wigner function is positive, that its inequality cannot be violated. However, this paper has been shown since then to be completely wrong, even if it was written by John Bell. And in fact, this paper attracted quite a lot of attention and has been criticized by many other papers, which are wrong as well. And this is really a fascinating story. And if you are interested in this funny story, I have told this story in this paper that you can find on the web. So in fact, the situation has been completely clarified by Revzen only quite recently in 2004 and 2006. And he has shown that Bell inequality can be violated even if the Wigner function of a system is positive. So in some sense, the positivity of the Wigner function does not necessarily mean that the system is classical or stochastic. And I'm just giving you one example that I have adapted to the context of cosmology. So suppose you have the Planck map. From the Planck map, you can measure, let's say, the Fourier component of curvature perturbation or the Fourier component of the position operator, which is given in terms of the creation and annihilation of which appear in the expression of the curvature perturbation by this expression. So this operator is Hermitian, therefore it's an observable. A priori, it's a valid observable. You can see it, you can observe it, you can detect it in the sky. And of course, this is a continuous variable, so it has a continuous spectrum. But now, let's, since we want to discuss and mimic what Bell did, we want to deal with discrete variables, spin variables, because you know that the Bell inequalities is very often formulated in terms of spin variables. So,
Professor Martin, I fear that there's no time left, so can you please?
Yes, I am coming to the end. I have,
okay, fine.
If
thank you.
I have 1 or 2 minutes, and I am coming to the
okay, thank you.
No problem. So, yes, you can define these fictitious spin operators, which allows you from a continuous variable to extract discrete variable plus or minus 1. Well, let me skip this. So this means that from a continuous quantity that you can extract on the sky, you can define an effective or pseudo spin operators, and from that you can mimic you can mimic a cosmic Bell experiment. And the question is whether, given those operators, the Bell inequality can be violated. And with Vincent Venin, we have shown that this is indeed the case. So this means that this is an explicit example which shows that even if the Wigner function is positive, there exist classes of operators that can lead to non-classical properties. So these operators are more complicated than simple powers of curvature perturbation, but hence, in principle, the quantum properties of cosmological perturbation are observable. So now my last slide, whether we can do it in practice or not. So the Z component that I was very quickly trying to introduce can a priori be measured, but the other component of the spin variable I think cannot be measured in practice because they involve the decaying mode, which is very small and cannot be seen in practice. And in addition, the whole thing is formulated in Fourier space. So because you are in practice, you cannot measure two non-commuting quantities, you also in principle, you could mimic this Bell inequality and see a quantum signature of the perturbation. In practice, you cannot do it. So maybe a way out, and I will finish with that, is to measure only the Z component that depends only on the growing mode, but at different times. This leads to another class of quantum inegalities that are known as the Leggett-Quark inequality, and maybe they are the way out. And with Vincent Venin, we have recently checked that the Leggett-Quark inequality are indeed violated for spin operators placed in a two-mode squeezed state. So since my time is out, I leave you with these conclusions that you can read and are just a recap of what I have said. Thank you for your attention.